Welcome to my talk in which I present our work on real-time predictive kinematics control of redundancy. What is the motivation of our work? Recently, we integrated a collaborative robot in a logistics facility. To achieve intuitive robot motions for human coworkers, we planned the robot motions in Cartesian space instead of configuration space. A sequence of Cartesian space waypoints is interpolated by a trajectory planner, and a subsequent differential inverse kinematics algorithm computes the joint velocity control commands. Our contribution is within the differential IK. Most of nowadays collaborative robots have a redundant kinematic design for more flexibility, and so does our Franca Emica robot. For these systems, the IK are not uniquely defined, and therefore the following equation is used. The joint velocity command is a sum of two components. The first tracks a given Cartesian space trajectory. The second optimizes a secondary objective L with gradient descent, however, only in the null space of the trajectory tracking task to not disturb it. We refer to this standard approach just shown as local because the control vector U only takes the current robot state into account. This is computationally cheap and thus real-time capable. However, the approach only reacts instantaneously. That is, for instance, if the secondary objective is obstacle avoidance, the control command U to avoid a collision would only be computed when the robot is already close to the obstacle. In contrast to that, global IK follows a predictive approach and computes U with optimal control. That is, the effect of U on future robot states is taken into account. However, the global approach is computationally expensive and thus not real-time capable. Our goal is to compute differential IK for redundant robots that optimize a secondary objective. Thereby, we follow a model predictive control approach. The objective is to minimize a given cost function L over a defined time horizon T PKC, and the differential IK of the local approach are a constraint of the optimization. That way, we get both a predictive and real-time capable algorithm. There has already been work in this direction. What is our contribution? State-of-the-art approaches most often use indirect methods to solve the optimal control problem. We did a benchmark and show that the direct shooting method performs best. Instead of numerically approximated gradients, we derive the analytical gradients to solve the optimization, which is required for an efficient real-time capable implementation. We use acceleration level IK instead of velocity level IK to get smoother joint velocity control signals. State-of-the-art approaches most often use simplified objectives and constraints to get a QP problem that can be solved efficiently. We propose a multi-threaded implementation that allows us to use nonlinear objectives and constraints, for example, required for collision avoidance, and still we are real-time capable. We implement our approach in the Predictive Kinematics Controller, the PKC. I will now present the methods we used and the results achieved. I will show the results with this application scenario. A four-link manipulator moves the end effector from a current pose to a goal pose. Close to the point-to-point path, there is a spherical obstacle. Our secondary objective is collision avoidance. The general benefit of the PKC is shown in this animation. The light blue robot shows our PKC controller. The green robot shows a local IK approach, the ASC, and the black robot shows an approach without secondary objectives, the RMRC. Our PKC approach in light blue adapts the robot motion early, while the local ASC approach in green only reacts locally, which leads to high collision avoidance costs that are defined by the proximity of the robot to the obstacle. The RMRC does not include collision avoidance as a secondary objective, and thus the robot crashes. We benchmarked different methods to solve the MPC, a direct collocation, a direct shooting, and an indirect gradient method. We did the benchmark with 50 randomly sampled point-to-point motions. The direct shooting method has the lowest relative computation time of 2.6 and was thus chosen for the implementation of the PKC. We derived the analytical gradient information for the optimization problem, which is input to the interior point solver that we used. The derivation of the various gradients is involved. For example, in this formula, you see the derivation of the pseudo-inverse of the Jacobian. I refer to our paper for the analytical gradient derivations. Solving the presented scenario with the direct shooting method requires 10 seconds computation time with analytic gradients, however 700 with numerically approximated ones. When using velocity level IK as the equation in the orange box, one gets jerky discontinuous control signals between the time horizons of the MPC. We tackle this problem with acceleration level IK as the equation in the light blue box. The bottom diagram shows the joint velocity control commands for the fourth joint of the presented application scenario. Our formulation with acceleration level IK in light blue is smoothest. The low-level control of our Franca Imica robot runs at 1 kHz. The MPC horizons cannot be solved at this rate. Instead of simplifying the MPC problem, we use a multi-threaded implementation. Besides the real-time thread, we have a parallel MPC thread that runs at 10 Hz and that solves MPC horizons of 1 second. This video shows the real-time capability of our approach. We apply the PKC on a Franca Imica robot, and the secondary objective is to maximize manipulability. On the top, you see the two local approaches introduced earlier. On the bottom left, you see our approach. The bottom right shows the manipulability measure. Our approach, shown in light blue, maximizes the manipulability best. Thank you for your attention.